Hello there, and welcome to the Slumber Science Society. Maybe you've had a long day, or perhaps you simply find peace in drifting through stories of Earth's most mysterious places. Either way, tonight's journey is for you. Tonight we descend into the deepest place on Earth, a realm of crushing pressure and eternal darkness called the Challenger Deep. A place so far beneath the waves that Mount Everest could fit inside with room to spare. It rests in silence at the bottom of the Mariana Trench, where the ocean floor drops away into a V-shaped canyon deeper than any other point accessible to humans. The Challenger Deep holds mysteries we're only beginning to understand, each one stranger and more beautiful than the last. If you enjoy these gentle journeys through science and exploration, consider liking, subscribing, or sharing a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, if you're ready, let's begin our descent. Imagine sinking slowly through layers of blue. The sunlight fades gradually as you drift downward, first through the bright surface waters where dolphins play and sailboats glide. Then deeper, into the twilight zone where the light grows dim and uncertain, where strange fish with enormous eyes hover in the gloom. Deeper still, past the last whispers of sunlight, into complete and total darkness. Down, down, down. The pressure builds with every meter. Your ears would feel it first, then your entire body, compressed by the weight of an entire ocean pressing in from all sides. At 10 meters down, you'd feel the pressure of 2 atmospheres. At 100 meters, 11 atmospheres. At 1,000 meters, where the last traces of sunlight surrender to blackness, you'd experience 101 atmospheres of pressure. But we're going much deeper than that. We're descending to a place where the pressure reaches 1,086 atmospheres. 15,750 pounds per square inch. 8 tons of force pressing on every single square inch. It's a pressure so immense it would crush almost anything in an instant, collapse submarines like tin cans, compress air until it becomes liquid. Yet life exists there. And humans have been there too, visiting this alien realm at the very edge of what's possible. The Challenger Deep rests at coordinates 11 degrees, 21 minutes north latitude, and 142 degrees, 12 minutes east longitude. If you were to travel to the western Pacific Ocean, about 200 kilometers east of the Mariana Islands, you would find yourself floating above the deepest known point in Earth's oceans. Below you, the seafloor would drop away into the Mariana Trench, a massive scar in the ocean floor stretching 2,550 kilometers in a graceful crescent shape. The trench itself is 69 kilometers wide at its broadest point, a vast submarine canyon with walls that slope down at different angles, steeper on the western side, gentler on the east. But even the sides of the trench aren't the deepest part. At the very bottom of this already impossibly deep canyon, there's a place where the floor drops even further. This is the Challenger Deep, named after a British sailing ship that first measured these depths over 150 years ago. The exact depth has been measured many times, and the numbers vary slightly depending on where precisely you take the measurement and how you account for the density of water at different temperatures and salinities. Modern measurements place the deepest point somewhere between 10,911 meters and 10,994 meters below sea level. Let's use the commonly cited depth of 10,984 meters, which equals roughly 35,850 feet, or about 6.8 miles straight down. To help understand this depth, imagine Mount Everest, Earth's tallest mountain, standing 8,849 meters above sea level. If you could somehow lift Everest and drop it into the Challenger Deep, the peak would still be over 2,000 meters underwater. More than a mile underwater. The mountain would disappear entirely beneath the waves, swallowed by the abyss. Or think of it another way. If you were to drop a weighted object from the surface, letting it sink at a steady rate of 1 meter per second, it would take more than 3 hours to reach the bottom. 3 hours of continuous falling through darkness and pressure and cold. 3 hours to cross a distance that light itself covers in less than 1/100th of a second. The shape of the Challenger Deep is not a simple hole or pit. It's more like a crescent-shaped slot cut into the already deep floor of the Mariana Trench. Imagine a valley within a valley, a depression within a depression. The trench itself forms a long arc, and at several points along this arc, the floor dips even deeper. The Challenger Deep is the most significant of these depressions, a place where tectonic forces have pushed the seafloor down to its absolute limit. At these depths, the temperature hovers just above freezing, between 1 and 4 degrees Celsius. Cold, but not quite frozen, kept from turning to ice by the immense pressure and the slight warmth that seeps up from the Earth's interior far below. The water is nearly still down there, with only the slowest currents drifting through. It's a place of profound calm, where nothing moves quickly, where everything happens in slow motion. The sediment that covers the floor is called diatomaceous ooze. It's made of tiny silica skeletons, the remains of microscopic organisms called diatoms that once lived near the surface, died, and slowly drifted down through thousands of meters of water. It takes these particles decades, sometimes centuries, to make the journey from sunlit waters to the abyssal plain. By the time they reach the Challenger Deep, they've passed through countless layers of ocean, been scattered by currents, consumed and excreted by deep-sea creatures, broken down into the finest powder. Diatoms themselves are remarkable organisms. They are single-celled algae that encase themselves in intricate glass shells made of silica, the same compound found in sand. Each species has its own unique shape. Some look like pillboxes, others like stars or chains of connected cells. Under a microscope, they are beautiful, geometric patterns etched in glass at a microscopic scale. Artists and microscopists in the Victorian era were fascinated by them, creating detailed illustrations of their forms. When a diatom dies, its soft cellular contents decay, but the glass shell remains. Being denser than water, it sinks. Slowly, gradually, it descends through the water column. Other organisms eat it, extract any remaining organic matter, and excrete the shell, which continues sinking. Bacteria colonize it. Chemical processes etch its surface. By the time it reaches the bottom, it may have been transformed many times, broken into smaller fragments, but the silica remains. In some parts of the ocean, where diatom productivity at the surface is particularly high, the seafloor is covered with thick layers of diatom ooze, sometimes hundreds of meters deep. These deposits can eventually become rock, compacted and cemented over millions of years into a type of stone called diatomite. Humans mine diatomite for industrial uses. It's used in filters, in toothpaste as a mild abrasive, in swimming pool filtration systems, even in dynamite as an absorbent for nitroglycerine. But at the Challenger Deep, the accumulation is slower. The surface waters above the Western Pacific are less productive than some other regions, so fewer diatoms rain down. The sediment accumulates at perhaps 1 to 2 millimeters per thousand years, sometimes even slower. This means the top layer of sediment, the surface you'd touch if you could reach down and brush it with your fingers, might be thousands of years old. The layer a meter below might be millions of years old. This sediment accumulates slowly, building up at a rate measured in millimeters per thousand years. The floor you'd stand on, if you could stand there, would be soft and fine, a pale gray or white powder that would puff up in clouds at the slightest disturbance. Its ancient material, some of it millions of years old, compressed under its own weight and the weight of the ocean above. Within these layers lies a record of the ocean's history, changes in temperature, in circulation patterns, in the types of organisms living at the surface. Scientists who study these sediment cores can read the ocean's past like a book written in microscopic shells. No sunlight reaches this depth. Not a single photon. The twilight zone of the ocean, where faint traces of light can still penetrate, ends at around 1,000 meters. Even in the clearest ocean water, even at noon on a cloudless day with the sun directly overhead, light cannot penetrate deeper than about 1,000 meters. And by that depth, it's so faint that only the most sensitive instruments can detect it. The reason is absorption and scattering. Water molecules absorb light energy, converting it to heat. The longer the light travels through water, the more it's absorbed. Different wavelengths are absorbed at different rates. Red light, with its longer wavelength, is absorbed first, disappearing within the first few meters. This is why everything looks blue underwater in shallow water. The red wavelengths have been filtered out, leaving only blue and green. As you go deeper, orange disappears, then yellow, then green. By 200 meters, only blue light remains, and even that is fading rapidly. Blue light, with its shorter wavelength, penetrates deepest, but even blue cannot reach more than 1,000 meters in the very clearest conditions. And the water at the surface of the Central Pacific is among the clearest in the world, far clearer than coastal waters clouded with sediment and plankton. Below 1,000 meters, it's absolute darkness, unbroken and complete. Not dim, not shadowy, but completely, utterly black. No eyes, no matter how sensitive, could see anything. No plant could photosynthesize. The sun, that massive fusion reactor that powers almost all life on Earth's surface, has no influence here. Its energy simply cannot reach this far. The only light that exists down there comes from living creatures, bioluminescent organisms that generate their own glow through chemical reactions within their bodies. Certain species of fish, jellyfish, and squid produce light through a reaction involving a chemical called luciferin and an enzyme called luciferase. When luciferin is oxidized in the presence of luciferase, it emits light, usually blue or green because those colors travel farthest in water. But even these lights are rare and dim at the greatest depths, brief flashes in an ocean of blackness. Most bioluminescence occurs in the twilight zone and upper reaches of the midnight zone, between 200 and 2,000 meters. Below that, and especially in the Hadal zone below 6,000 meters, bioluminescence becomes increasingly rare. The energy cost of producing light outweighs the benefits in an environment where organisms have largely abandoned vision anyway. It's a world that exists in permanent night, where sight means almost nothing, where creatures navigate by touch and sound and chemical signals. Where the very concept of day and night becomes meaningless, because the sun's cycle never reaches this far down. It's always midnight in the Challenger Deep, always has been, always will be. The pressure at this depth is what makes it truly extreme. 1,086 bar. That's 1,087 atmospheres if you count the one atmosphere at sea level. Or 15,750 pounds per square inch. To put that in perspective, a typical car tire is inflated to about 32 pounds per square inch. The pressure at the bottom of the Challenger Deep is nearly 500 times greater than your car tire. Imagine 8 tons of weight pressing down on every single square inch of surface. On your hand, on your chest, on every part of you. That pressure would compress air until it behaved like a liquid. It would crush submarines, collapse human lungs, break bones, rupture cells. Only specially designed vessels can withstand it, built from the strongest materials, engineered to distribute the force evenly across their surface. And yet, despite this crushing environment, despite the darkness and the cold and the scarcity of food, life has found a way to exist there. Not just to survive, but to thrive in its own strange way. Creatures that have adapted over millions of years to conditions that would kill most other organisms in seconds. The Challenger Deep is not just a geographical curiosity, not just a record in a book of extremes. It's a frontier, a place that pushes the boundaries of what life can endure and what humans can achieve. It represents the absolute edge of Earth's ocean, the deepest you can go while still remaining on this planet. And to understand how we know about this place, how we discovered it and began to explore it, we need to go back in time. Back to an era when the ocean depths were as mysterious as the surface of the moon. Back to the age of Victorian exploration, when a British sailing ship set out on an unprecedented journey to map the hidden contours of the seafloor. The year was 1872. Queen Victoria sat on the throne of the British Empire. Charles Darwin had published his theory of evolution just over a decade earlier. The Industrial Revolution was transforming the world with steam engines and telegraph lines. But the ocean depths remained almost completely unknown, a vast frontier untouched by science. Most scientists of the era believed the deep ocean was lifeless, a barren wasteland where nothing could possibly survive. The pressure was too great, the darkness too complete, the cold too extreme. Some thought the water itself became so compressed at depth that it turned solid, creating a dense, impenetrable layer that nothing could pass through. But there were hints that this view might be wrong. Occasionally, when laying telegraph cables across the Atlantic Ocean, crews would bring up samples from the seafloor, and these samples sometimes contained strange creatures. Living organisms pulled up from depths previously thought uninhabitable. These discoveries sparked curiosity and debate. Perhaps life could exist in the deep ocean after all. Perhaps there was an entire world down there waiting to be discovered. The British government decided to find out. They commissioned a scientific expedition unlike any attempted before. They converted a Royal Navy corvette, a three-masted sailing ship called HMS Challenger, into a floating laboratory. They removed most of the ship's guns and installed scientific equipment in their place. Dredges for collecting seafloor samples. Thermometers for measuring water temperature. Chemical apparatus for analyzing seawater. Microscopes for studying tiny organisms. Preservation tanks for storing specimens. The ship departed Portsmouth, England, on December 21, 1872. On board were 243 officers and crew, plus a team of 6 scientists led by Professor Charles Wyville Thompson. The captain, George Strong Nares, was an experienced naval officer who would later gain fame for Arctic exploration. The mission was simple in concept but staggering in scope. Circumnavigate the globe. Visit every major ocean. Take measurements of depth, temperature, currents, and marine life. Collect samples from as many locations as possible. Map the hidden topography of the seafloor. Prove once and for all whether life existed in the deep ocean. The expedition lasted 3 years, 7 months, and 16 days. The Challenger sailed over 127,653 kilometers, roughly 3 times the circumference of Earth. The ship made 713 days at sea, visiting virtually every corner of the world's oceans. From the frigid waters of Antarctica to the tropical Pacific, from the Atlantic to the Indian Ocean and back again. Life aboard the Challenger was governed by routine and discipline, the way of all sailing ships in that era. The crew rose before dawn, scrubbed the decks, checked the rigging, adjusted the sails to catch the best wind. The scientists worked around the clock when conditions permitted, taking measurements at different times of day and night to understand how the ocean changed with the sun's cycle. They developed techniques as they went, inventing new methods for deep-sea sampling because none existed before. Every station, every measurement, was pioneering work. They learned to estimate depths by the time it took for a weighted line to reach bottom, to judge water temperature by the expansion of mercury in specially designed thermometers, to preserve delicate specimens in alcohol so they could be studied back in England. The ship crossed the equator multiple times, sailing from winter to summer and back again, experiencing every climate zone. In the tropics, the heat was oppressive, the decks so hot they burned bare feet, the air thick with humidity. In the Southern Ocean near Antarctica, ice formed on the rigging, winds howled through the masts, and waves towered higher than the ship itself. The crew endured seasickness, exhaustion, and occasional injuries from the dangerous work of handling heavy equipment on a pitching deck. But they persisted. This was the age of Victorian exploration, when Europeans ventured to every corner of the globe, driven by curiosity, imperial ambition, and the belief that science could unlock nature's secrets. The Challenger expedition embodied that spirit, combining naval precision with scientific inquiry in service of expanding human knowledge. It was arduous, exhausting work. The crew would lower dredges and nets thousands of meters into the depths on hemp ropes, then spend hours hauling them back up by hand, muscles straining, rope burning their palms. Sometimes the equipment would catch on rocks or break free entirely, sending months of work to the bottom. Other times they would bring up treasures, strange creatures never before seen, sediment samples that revealed the ocean floor's composition. Each dredge haul took hours. The crew would attach the dredge, a heavy metal frame with a bag to collect samples, to thousands of meters of rope. They'd lower it carefully, watching the rope pay out coil by coil. When it reached bottom, they'd drag it along the sea floor for a distance, then begin the back-breaking work of hauling it up. 20 or 30 men would line up, gripping the rope, pulling in rhythm to sea shanties that helped coordinate their efforts. Pull, step, for hours on end, until finally the dredge emerged dripping from the depths. They took hundreds of measurements, collected thousands of specimens. They discovered over 4,700 new species of marine life. They mapped temperature gradients and ocean currents. They measured salinity and chemical composition. They transformed oceanography from speculation into rigorous science. And on March 23, 1875, at a location they designated Station 225, they made a measurement that would echo through history. The Challenger was sailing in the Western Pacific, south of Guam and the Mariana Islands. They lowered a sounding line, a weighted rope with careful markings to measure depth. The line went down, and down, and down, far deeper than any previous measurement. When they finally reached bottom and calculated the depth from the length of rope played out, they recorded a depth of 4,475 fathoms. A fathom is 6 feet, an old maritime measurement based on the span of a man's outstretched arms. 4,475 fathoms equals 26,850 feet, or about 8,184 meters. It was, at the time, the deepest point ever measured in the ocean. The crew knew they had found something significant, a place where the sea floor dropped away into unimaginable depths. They noted the location carefully in their logs and continued on their journey. When the Challenger returned to England on May 24, 1876, the expedition was hailed as a triumph. The scientists spent the next 2 decades analyzing their findings, publishing 50 thick volumes of reports that laid the foundation for modern oceanography. Among their many discoveries, that deep sounding in the Western Pacific stood out. They had found the deepest known point in the ocean. In honor of their achievement, this deep place was eventually named the Challenger Deep. The ship that had circled the world, endured storms and doldrums, collected specimens from pole to pole, would be remembered forever in this darkest corner of the sea. But the Challenger's measurement was only the beginning. The depth they recorded, while impressive, turned out to be incorrect. They weren't actually at the deepest point, and even where they were, the seafloor was deeper than their measurements suggested. The techniques of the 1870s, while groundbreaking for their time, lacked the precision of modern methods. It would take decades more exploration, new technologies like sonar and echo sounding, before scientists could accurately map the ocean floor and pinpoint the true deepest location. Those later surveys would find that the Challenger Deep reaches far greater depths than the Challenger's crew measured, extending down over 10,900 meters, nearly 3 kilometers deeper than they thought. But their achievement remains remarkable. With nothing but hemp rope and determination, they ventured into unknown waters and found a place that challenged every assumption about the ocean. They opened the door to deep-sea exploration, inspiring generations of scientists to follow. And they gave us a name that still captures the imagination, the Challenger Deep, where the ocean reaches its absolute limit. To understand why the Challenger Deep exists, why this particular spot drops deeper than anywhere else on Earth, we need to look at the massive geological forces that shape our planet. Forces so powerful they move continents, raise mountains, and tear the seafloor apart. Earth's outer shell, the crust and upper mantle, is broken into enormous pieces called tectonic plates. These plates float on a layer of semi-molten rock deep below, drifting slowly across the planet's surface. Some plates carry continents. Others lie beneath oceans. They move at speeds measured in centimeters per year, about as fast as your fingernails grow. But slow doesn't mean gentle. When these plates collide, incredible forces come into play. Mountains rise. Earthquakes shake the ground. Volcanoes erupt. And in the ocean, the deepest trenches form. The Mariana Trench, and the Challenger Deep within it, exists because of a collision between two plates. The Pacific Plate, one of Earth's largest tectonic plates, is moving westward. It encounters the smaller Mariana Plate, and because the Pacific Plate is older, colder, and denser, it doesn't push the Mariana Plate aside. Instead, it dives underneath, sliding down into Earth's mantle in a process called subduction. Imagine two massive sheets of rock, each dozens of kilometers thick, pressing against each other. One begins to bend, to bow downward, forced by the relentless pressure. It descends at an angle, diving deeper and deeper into the planet's interior. As it descends, it drags the seafloor with it, creating a deep, V-shaped depression. This is how oceanic trenches form. The Pacific Plate being subducted beneath the Mariana Plate is ancient by geological standards. About 170 million years old, formed during the Jurassic period when dinosaurs roamed the Earth. Over those vast stretches of time, the plate has cooled and contracted, becoming dense and heavy. This density helps pull it down, adding to the forces driving subduction. The subduction zone extends far below the Mariana Trench. The Pacific Plate continues descending at an angle of about 45 degrees, plunging hundreds of kilometers into the mantle. As it goes, it heats up from the surrounding rock. Water trapped in the plate's minerals is released, rising upward and triggering volcanic eruptions. This is why the Mariana Islands, just to the west of the trench, are volcanic. They are born from the water and heat released by the descending plate. The trench itself, that V-shaped canyon, forms where the two plates meet. The bending of the Pacific Plate creates a depression, and the steepness of its descent determines how deep that depression becomes. At the Challenger Deep, The geometry is just right. The plate descends at the perfect angle. The forces balance in just the right way to create the deepest point. The trench is asymmetric because of this geometry. The western wall, on the Mariana Plate side, rises more steeply. It's the edge of the overriding plate, thrust upward by the collision. The eastern wall, on the Pacific Plate side, slopes more gently. It's the outer rise of the plate as it begins to bend downward. This process happens continuously, though the motion is imperceptibly slow. The Pacific Plate moves westward at about 7 to 11 centimeters per year. Each year, it advances just a few centimeters. But over millions of years, it has traveled thousands of kilometers. And the trench, the depression created by this motion, slowly deepens. The Mariana Trench has been forming for at least 50 million years, possibly longer. Throughout that time, the Pacific Plate has been diving into the mantle, and the trench has been growing deeper. Sediment accumulates on the bottom, but the plate's motion carries it down and away, preventing the trench from filling in. The region is seismically active. Earthquakes occur frequently as the plates grind against each other, releasing built-up stress. Most are small, barely noticeable. But occasionally, massive quakes strike, powerful enough to generate tsunamis that race across the Pacific. The subduction zone can produce some of the largest earthquakes on Earth, magnitude 9 and above, when huge sections of the plate suddenly slip. The Challenger Deep sits in the middle of this vast tectonic boundary, a place where the planet's interior meets the ocean in dramatic fashion. The deepest point is not static. Over geological time, it may shift as the plates continue their motion, as the geometry changes, as the subduction process evolves. Millions of years from now, the Challenger Deep might be somewhere else entirely, or it might no longer exist, replaced by a new deepest point elsewhere. But for now, this is where Earth's ocean reaches its maximum depth. This is where the forces of plate tectonics have carved the deepest accessible point on the planet. A place born from the collision of ancient rocks, shaped by processes that have been ongoing for millions of years and will continue for millions more. The timescales involved are almost impossible to comprehend. Think of it this way. The Pacific Plate that's currently at the Challenger Deep was at the surface of the ocean, newly formed at a mid-ocean ridge 170 million years ago. That was during the Middle Jurassic period. Stegosaurus and Allosaurus roamed the land. The Atlantic Ocean was just beginning to open. Flowering plants didn't exist yet. When that piece of seafloor formed, the supercontinent Pangaea was still breaking apart. India was an island drifting northward, not yet collided with Asia to form the Himalayas. The Rocky Mountains didn't exist. Birds had only just evolved from small theropod dinosaurs. The climate was warmer than today, with no polar ice caps, and sea levels were higher, flooding large portions of what are now continents. Since then, that plate has traveled across the Pacific, carrying its cargo of sediment and fossils and trapped water. It has moved perhaps 10,000 kilometers, a quarter of the way around the Earth, gradually cooling and contracting. As it traveled, the ocean floor accumulated sediment, layer upon layer of microscopic shells and volcanic ash and cosmic dust settling from above. These layers record the history of the Pacific, changes in ocean temperature, fluctuations in sea level, periods of volcanic activity, even asteroid impacts that left their signature in the sediment. The plate has witnessed the evolution of whales, the rise and fall of countless species, the spread of coral reefs, and the dramatic shifts in global climate that have marked the past 170 million years. It has been home to countless generations of marine life, from the smallest bacteria to the largest predators. And through all of this, it has been moving steadily westward, driven by the inexorable forces of mantle convection. And now, finally, it returns to the interior, diving back into the mantle where it will be recycled, melted, and eventually rise again as new volcanic rock. The sediment on its surface, those layers recording millions of years of history, will be subducted along with the plate, carried down into the mantle where heat and pressure will transform them. Some will be scraped off and added to the overriding plate, building up the seafloor on the western side of the trench. But most will descend into the depths, eventually melting and mixing with the mantle material. The water trapped in the plate's minerals will be released as it heats up, rising upward to trigger volcanic eruptions in the Mariana Islands. The carbon in the sediment may eventually return to the atmosphere through volcanic gases, completing a cycle that takes hundreds of millions of years. The plate itself will be assimilated into the mantle, its atoms scattered and mixed, eventually to be recycled as new oceanic crust at some distant spreading ridge. This is the grand cycle of plate tectonics, the process that has shaped Earth's surface for billions of years. The Challenger Deep is just one small part of this vast system, a place where we can witness the plate's final descent before it vanishes into the mantle. This is the rock cycle on a planetary scale, driven by heat from Earth's interior and the slow but inexorable motion of tectonic plates. The Challenger Deep is just one small part of this enormous system, a place where we can glimpse these deep processes in action. And while the geological forces are powerful beyond measure, there's something almost peaceful about their pace. Nothing happens quickly. The plates move centimeters per year. The trench deepens millimeters per century. Earthquakes strike in sudden bursts of energy, but they are separated by decades or centuries of relative calm. It's a patient, methodical reshaping of the planet, a dance of rock and time that has been going on for billions of years. So when you imagine the Challenger Deep, don't just picture a hole in the seafloor. Picture the meeting of two ancient plates, one diving beneath the other. Picture the forces involved, powerful enough to move continents, but spread out over such vast areas and such long timescales that they seem almost gentle. Picture the slow accumulation of sediment, the gradual deepening, the imperceptible motion that continues every moment of every day, year after year, millennium after millennium. This is how Earth works. This is how mountains rise and valleys form, how oceans open and close, how the very face of the planet changes over deep time. And the Challenger Deep, that small crescent-shaped depression in the Western Pacific, is one of the most dramatic expressions of these forces, a place where geology reveals itself in its most extreme form. At the bottom of the Challenger Deep, conditions exist that would be instantly fatal to unprotected humans. The pressure alone would crush you before you could take a single breath. But beyond the pressure, there are other extremes that make this environment one of the most hostile places on Earth. The cold is profound. Water temperature at the bottom hovers between 1 and 4 degrees Celsius, just above the freezing point of seawater. The ocean doesn't freeze at 0 degrees like fresh water. The salt dissolved in it lowers the freezing point to about -2 degrees Celsius. So the water at the bottom is cold, but not frozen, kept liquid by its salt content and, paradoxically, by the immense pressure, which also raises the freezing point slightly. This cold isn't the biting, wind-driven cold of a winter day. It's a deep, penetrating cold that would leach heat from your body in seconds. Without the thick insulation that deep-sea submersibles provide, you'd lose body heat faster than you could generate it, even if you could somehow survive the pressure. Where does this cold water come from? It originates at the poles. In the Arctic and Antarctic, surface water cools in winter, becomes denser, and sinks. This dense, cold water flows along the ocean bottom, spreading slowly through the abyssal plains. It takes hundreds or even thousands of years for water from the poles to reach the Challenger Deep, but eventually it arrives, carrying its frigid temperature to the deepest places. There's also a slight warming from below. Heat from Earth's interior, from the decay of radioactive elements in the mantle and core, seeps upward through the crust. This geothermal heat is tiny compared to the cooling effect from above, but it's enough to prevent the bottom from reaching absolute zero. In some places, near hydrothermal vents where magma approaches close to the seafloor, temperatures can soar to hundreds of degrees. But the Challenger Deep is far from any such vents. Here, the geothermal contribution is minimal, just a gentle warmth radiating through the rock. The darkness is absolute and permanent. No light from the sun reaches this depth. The deepest that sunlight penetrates, even in the clearest ocean water, is about 1,000 meters, and that's just faint traces of blue. The twilight zone extends from 200 to 1,000 meters, where light is present but too dim for photosynthesis. Below that, it's complete blackness. This isn't the darkness of night, where your eyes adjust and you can eventually make out shapes. This is the absence of light at a fundamental level. If you were there in a submersible with all the lights off, you would see absolutely nothing. Not shadows, not gradations of gray. Just perfect, impenetrable black in every direction. The only light that exists is bioluminescence, the chemical glow produced by living organisms. Some deep-sea creatures have evolved the ability to create light through chemical reactions within specialized organs called photophores. They use this light for various purposes: to attract prey, to communicate with potential mates, to startle predators, or to create counterillumination that makes them invisible against the faint glow from above. But even bioluminescence is rare at the deepest depths. Most of the creatures in the Hadal zone, the region from 6,000 to 11,000 meters that includes the Challenger Deep, don't bother with light. There's not enough benefit to justify the energy cost. Instead, they rely on other senses: touch, chemical detection, pressure sensitivity, sound. The water itself is remarkably clear at these depths. There's no sunlight to fuel photosynthesis, so no phytoplankton blooms cloud the water. The sediment is settled and undisturbed. If you could see down there, if you shone a light into the darkness, it would penetrate far into the gloom, illuminating particles suspended in the water column, perhaps catching the reflection of a passing amphipod or snailfish. But without a light source, you would be blind. Your eyes would be useless. You could stretch your hand in front of your face and see nothing. No shapes, no colors, no hint of your surroundings. The darkness would press in from all sides, complete and overwhelming. The pressure, though, is the defining characteristic of this environment. 1,086 bar. 15,750 pounds per square inch. To understand what this means, consider that every square centimeter of surface area at the bottom experiences the weight of about 1,100 kilograms pressing down on it. That's like having a small car balanced on every square centimeter. This pressure affects everything. It compresses gases until they behave differently. Oxygen becomes toxic at much lower concentrations. Nitrogen can dissolve into your tissues, creating a condition like extreme nitrogen narcosis. Carbon dioxide becomes so compressed it could form solid ice, even at these temperatures, if enough were present. The pressure affects chemistry and physics in subtle ways. Water itself becomes slightly denser, compressing about 5% compared to surface water. Sound travels faster because the water is more dense, moving at about 1,530 meters per second instead of the 1,500 at the surface. That's still far slower than light, but faster than sound in air by a factor of 4 or 5. Submarines and submersibles designed for shallow depths would implode instantly at this pressure. The hull would crumple like a tin can crushed in a fist. Only specially designed vessels can survive. They need to be built from materials like titanium or special steel alloys. They need to be shaped as perfect spheres to distribute the pressure evenly. They need thick walls, sometimes dozens of centimeters thick, to withstand the crushing force. The life support systems must be pressure balanced. Air inside the cruise sphere is kept at normal atmospheric pressure, around 1 bar. This means there's a pressure difference of over 1,000 bar between the inside and outside of the hull. The sphere must be strong enough to maintain this difference without failing. Windows are a particular challenge. Glass strong enough to resist this pressure must be incredibly thick. Some deep-sea submersibles use acrylic windows 20 or 30 centimeters thick, carefully shaped with taper so the pressure squeezes them more tightly into their frames. Even then, there's always a risk. At extreme pressure, materials behave unpredictably. Microcracks can propagate suddenly. Seals can fail. It's an environment that allows no mistakes. The sediment on the bottom is fine and soft. Diatomaceous ooze, as it's called, is made primarily of the silica shells of diatoms, microscopic algae that live near the surface. When they die, their shells sink slowly through the water column, taking decades or centuries to reach the bottom. By the time they arrive at the Challenger Deep, they've been broken down into an incredibly fine powder. This sediment accumulates slowly, perhaps a millimeter or 2 per 1,000 years. It's been building up for millions of years, forming layers that record the history of the ocean above. Within these layers are the remains of countless organisms, tiny foraminifera and radiolarians, microscopic zooplankton, fragments of larger creatures that sank from above. If you could scoop up a handful of this sediment and examine it under a microscope, you'd see intricate geometric shapes, the beautiful silica shells left behind by diatoms. Circles with radiating spines, elongated ovals, delicate chains of connected cells. Each one a tiny work of art, preserved in the sediment for eons. The sediment is also home to bacteria and other microorganisms, the base of the food web at this depth. They break down organic matter, recycle nutrients, and support the few larger animals that call the Hadal zone home. Life at the bottom is sparse but not absent, clinging to existence in this most extreme environment. No current moves quickly here. The water is relatively still, disturbed only by the slow, deep circulation that brings cold polar water to the abyss. Occasionally, a turbidity current might flow down from shallower areas, a dense mixture of water and sediment that pours down the continental slope like an underwater avalanche. But in the deep trenches, far from the continents, such events are rare. Instead, there's a profound calm, a stillness that has persisted for millions of years. The water barely moves. The sediment settles undisturbed. Time seems to slow down, stretched out by the crushing pressure and the cold and the darkness. This is the environment of the Challenger Deep. Hostile, extreme, alien. A place that seems designed to keep life out, to resist exploration, to remain hidden and unknown. And yet, despite all these extremes, life has found a way to exist here. And humans, driven by curiosity and the desire to explore, have built machines capable of reaching this impossible place. On January 23, 1960, 2 men descended into the Challenger Deep and became the first humans to reach the deepest point in the ocean. Their names were Jacques Piccard and Don Walsh. Their vessel was the bathyscaphe Trieste, and their journey would prove that humans could visit even this most extreme environment. The Trieste was not a submarine in the traditional sense. Submarines are military vessels designed to travel long distances underwater, to hunt other ships, to launch torpedoes or missiles. The Trieste was something different, a bathyscaphe, a deep-diving vessel designed for one purpose only, to descend to the greatest possible depths and return safely. The concept was invented by Jacques Piccard's father, Auguste Piccard, a Swiss physicist and engineer who had previously set altitude records in high-altitude balloons. Auguste understood that exploring the deep ocean required a completely different approach than conventional submarines. At extreme depths, the pressure was too great for traditional designs. A new kind of craft was needed. Auguste designed the bathyscaphe around a simple but elegant principle borrowed from ballooning. Instead of using compressed air for buoyancy like a submarine, the bathyscaphe would use a large tank filled with gasoline. Gasoline is lighter than water, providing buoyancy, but unlike air, it's incompressible. Squeeze it under enormous pressure, and it simply becomes slightly denser without changing volume dramatically. This meant the float could be built with relatively thin walls, since there was no pressure difference between the inside and outside. The crew would ride in a small, immensely strong sphere attached beneath this float. This sphere had to withstand the full pressure differential, keeping the occupants at normal atmospheric pressure while surrounded by water under extreme pressure. To do this, it needed to be built like a fortress, with incredibly thick walls and a perfectly spherical shape to distribute stress evenly. The original Trieste was built in Italy and launched in 1953. It was named after the city of Trieste, which at the time was a free territory disputed between Italy and Yugoslavia. The first pressure sphere was made of steel from the Italian city of Terni, but it wasn't strong enough for the deepest dives. In 1958, the United States Navy purchased the Trieste for $267,000. They recognized its potential for deep ocean research and exploration. The Navy transported it to San Diego and set about modifying it for an attempt on the Challenger Deep. The most critical upgrade was a new pressure sphere, manufactured by Krupp Steel Works in Essen, Germany. This sphere was a masterpiece of engineering. It measured 2.16 meters in diameter, just large enough for two people to squeeze inside. But its walls were 127 millimeters thick, over 5 inches of solid forged steel. The sphere was built in 3 sections, an equatorial ring and 2 hemispherical caps. These pieces were machined to incredibly tight tolerances and bolted together with heavy flanges. The entire assembly weighed 14.25 metric tons in air, though its weight in water was reduced to 8 metric tons due to buoyancy. The steel was specially formulated to withstand 1,250 kilograms per square centimeter of pressure, with a substantial safety factor built in. The Krupp engineers calculated every detail, tested sample materials under extreme conditions, and delivered a sphere that could theoretically survive pressures even greater than those at the Challenger Deep. The sphere had one viewport, a single thick block of acrylic glass tapered so that pressure would squeeze it more tightly into its frame. It was the only way to see outside, a small window perhaps 20 centimeters across. Everything else was steel, sealed tight against the ocean. The float above the sphere held 120,000 liters of aviation gasoline, divided into 11 separate buoyancy tanks. This massive volume of gasoline provided enough lift to bring the entire craft to the surface, even with the heavy steel sphere pulling it down. Seawater could enter and exit the float through open holes at the bottom, equalizing pressure and preventing the tanks from collapsing. For descent, the Trieste carried ballast, 18 metric tons of iron shot divided between 2 conical hoppers, one at the front and one at the rear. The shot was held in place by electromagnets. To descend, you simply sank, the weight of the iron pulled you down. To ascend, you released the iron shot by switching off the electromagnets. The shot would pour out through openings at the bottom of the hoppers, and the buoyant gasoline float would carry you back to the surface. This system was beautifully simple and inherently safe. If power failed, the electromagnets would stop working, the shot would release automatically, and the bathyscaphe would float up on its own. You couldn't get stuck at the bottom. Gravity itself was your backup plan. The Trieste also had 2 water ballast tanks at the front and rear, which could be flooded or emptied to adjust trim. Small electric motors powered propellers for horizontal movement, though these were mostly for fine positioning. The bathyscaphe wasn't designed to travel long distances horizontally. It went down and came up, and that was enough. Jacques Piccard, Auguste's son, served as the civilian operator and co-designer. He had worked with his father on developing bathyscaphes and knew the Trieste intimately. Lieutenant Don Walsh, a U.S. Navy submarine officer and qualified Navy diver, was chosen to accompany him. Walsh had trained extensively with the Trieste during the Navy's test dives and understood both its capabilities and its limitations. In October 1959, the Trieste was loaded aboard a freighter, the Santa Maria, and transported from San Diego to Guam. The plan was to conduct a series of progressively deeper test dives before attempting the Challenger Deep. Those test dives went well. The bathyscaphe proved reliable, descending to depths of thousands of meters and returning safely. Minor problems were fixed, systems were adjusted, and confidence grew. With each successive dive, they pushed a little deeper, learning how the bathyscaphe handled, how the systems performed under increasing pressure, where potential weaknesses might emerge. They dove to 1,000 meters, then 2,000, then 3,000. Each time, they checked the sphere for any signs of stress, inspected the gasoline tanks for leaks, tested the electromagnets that held the ballast. Each time, the Trieste performed flawlessly. The Krupp sphere held firm, the gasoline provided reliable buoyancy, the ballast system worked exactly as designed. Piccard and Walsh trained together, learning to work as a team in the cramped sphere. They practiced emergency procedures, rehearsing what they would do if power failed, if the ballast wouldn't release, if the window cracked. They studied the blueprints, memorized the location of every valve and switch, tested each other on the proper response to different scenarios. They also prepared mentally. Descending to 11,000 meters would take nearly 5 hours, followed by time on the bottom, then over 3 hours to ascend. 9 hours total in a steel sphere barely large enough for 2 people, with no way to exit until returning to the surface. They would be sitting in near-freezing temperatures, breathing air that grew steadily more humid and stale, dependent entirely on the integrity of the bathyscaphe. The psychological challenge was as significant as the physical one. They needed to remain calm and alert throughout the dive, ready to respond to problems but not so tense that they exhausted themselves. They talked through their fears, acknowledged the risks, and accepted them. This was exploration at its purest, venturing into the unknown with courage and careful preparation. By January 1960, Piccard and Walsh felt ready for the ultimate challenge. The Trieste had proven itself. They had trained extensively. The support systems were in place. It was time. On January 23rd, conditions were favorable. The sea was relatively calm. The Trieste was towed to a location above the Challenger Deep, coordinates carefully confirmed. The support ship, USS Wondank, stood by. Another vessel, USS Lewis, provided additional support. Everything was ready. Piccard and Walsh climbed into the cramped sphere. It was barely large enough for 2 people sitting side by side, surrounded by instrumentation, breathing in air that quickly grew stale and humid. The hatch was sealed from the outside, a heavy steel lid bolted shut. From that moment, they were committed. There was no way to open the hatch from inside under pressure. They would descend, reach the bottom, and return. Or they wouldn't. At 8:33 in the morning, they began flooding the ballast tanks. The Trieste settled deeper in the water, then slipped beneath the surface. The descent had begun. They sank slowly, carefully, at about 0.9 meters per second. Through the small viewport, they watched the water change color. First the bright blue of the surface, sunlight streaming through. Then deeper blue as the light faded. Then a twilight zone where strange fish with enormous eyes drifted past. Then blackness, complete and total. The hours passed slowly. 4 hours. 4.5. They were falling through an abyss, a darkness so profound it seemed to press against the tiny window. The temperature inside the sphere dropped as heat was conducted away through the steel walls. They wore warm clothing, but the cold still seeped in. After passing 9,000 meters, about 30,000 feet, there was a loud bang. The entire bathyscaphe shook. One of the outer acrylic windows, a small panel attached to the exterior for additional viewing, had cracked under the pressure. It wasn't the main viewport into the sphere itself that remained intact, but it was still alarming. Picard and Walsh faced a decision. They were already deeper than anyone had ever gone. They could release ballast and return to the surface, claiming a depth record. Or they could continue, trusting that the main viewport would hold, risking everything to reach the bottom. They decided to continue. The Trieste kept sinking. The pressure climbed higher. 10,000 meters. 10,500. 10,900. The depth gauge, calibrated for extreme pressures, showed numbers never before seen. Finally, after 4 hours and 47 minutes of descent, they felt a gentle bump. The Trieste had touched bottom. They were there, at the deepest accessible point in the ocean. The depth gauge read 11,521 meters, 37,799 feet. Outside the viewport, illuminated by the bathyscaph's lights, they could see the seafloor. A pale surface of fine sediment, undisturbed for eons. The lights cast a circle of illumination perhaps 10 meters across, beyond which everything faded into absolute blackness. The sediment was smooth, featureless, a flat plain extending in all directions. No rocks, no plants, no obvious signs of life at first glance. But as their eyes adjusted and they looked more carefully, they noticed movement. Small disturbances in the sediment, tracks or burrows left by creatures. And then they saw it, what appeared to be a flatfish, something resembling a sole or flounder, about 30 centimeters long. It was lying on the sediment, camouflaged against the pale background. As they watched, it slowly moved, propelling itself with gentle undulations, then disappeared out of the light's reach. They had expected complete lifelessness, the prevailing theory among scientists at the time. The pressure was too great, the environment too extreme. Nothing could possibly survive. But here was proof, visible through their window, that life existed even here. Something was alive at the bottom of the Challenger Deep. They also saw what might have been shrimp-like creatures, difficult to identify in the murky light and through the small viewport. The water stirred up by their landing swirled with particles, making observations challenging. But there was no doubt, organisms of some kind inhabited this place. Picard made notes, describing what they saw. Walsh took photographs, though the quality would be limited by the available light and the small window. They collected observations on temperature, the condition of the water, the nature of the sediment. Every detail mattered. This might be the only time humans reached this depth for decades, and they needed to document everything possible. This observation would later be questioned. Marine biologists pointed out that fish shouldn't be able to survive below about 8,000 to 8,500 meters. Beyond that depth, The pressure makes their body chemistry impossible. The salt concentration in their tissues can't match the external pressure without making them hyperosmotic, literally too salty to function. So what did Pickard and Walsh see? They may have mistaken an invertebrate for a fish. Sea cucumbers and other creatures can look fish-like in the dim light. Or perhaps they saw something else entirely, a shadow, a piece of debris, something stirred up by their descent. Walsh himself later admitted that their biological knowledge was limited, and the observation could have been a mistake. But whether they saw a fish or not, they proved something more important. Life existed at the bottom of the Challenger Deep. They saw movement, organisms of some kind. The deep ocean was not lifeless. It was inhabited, even at this extreme depth. They stayed on the bottom for 20 minutes. 20 minutes at the deepest point on Earth, a record that would stand for over 50 years. They took photographs, though many didn't turn out well in the murky water. They made observations, recorded data, absorbed the magnitude of their achievement. The temperature inside the sphere had dropped to 7 degrees Celsius, just above the temperature outside. The cold steel walls provided little insulation. Their breath formed faint clouds in the air. But they were warm enough, protected by the layers of clothing they wore. Communication with the surface ship, USS Wondank, was maintained through an underwater telephone system using sonar. Sound travels well in water, much faster than in air, at about 1,600 meters per second. But even at that speed, it took roughly 7 seconds for a message to travel from the Trieste to the surface, and another 7 seconds for the reply to come back. They could talk to the ship, but with a 14-second delay between question and answer. After 20 minutes, it was time to ascend. They had proven what they came to prove. Now they needed to return safely. Pickard activated the ballast release. The electromagnets switched off. The iron shot poured out of the hoppers, disappearing into the darkness, falling to the sediment below. With the weight gone, the Trieste began to rise. The ascent was faster than the descent, 3 hours and 15 minutes instead of nearly 5. The gasoline float pulled them upward, accelerating slowly as they rose and the pressure decreased. Through the viewport, they watched the darkness gradually lighten. First a faint glow, barely perceptible. Then twilight. Then the deep blue of the upper ocean. At 1:31 in the afternoon, the Trieste broke the surface. They had been underwater for 8 hours and 48 minutes. They had reached the deepest place on Earth and returned. Don Walsh and Jacques Pickard had accomplished something no one else had ever done, opening a new frontier for human exploration. The Navy later revised the depth measurement, accounting for variations in water density, temperature, and salinity. The corrected depth was 10,916 meters, about 35,814 feet. Still the deepest point, still a record, but slightly less than the initial reading. Modern measurements using sophisticated sonar have placed the deepest spot between 10,911 and 10,994 meters, depending on exactly where you measure. But the exact number doesn't diminish what Pickard and Walsh achieved. They proved that humans could reach the deepest ocean. They demonstrated that a properly designed craft could withstand the pressure. They showed that exploration was possible even in this most extreme environment. And they did it with technology from the 1950s, with steel and gasoline and electromagnetic ballast releases, with courage and careful engineering. The Trieste would dive again, used for other research missions, including a search for the wreckage of the USS Thresher, a nuclear submarine that sank in 1963. But it never returned to the Challenger Deep. That single dive remained unique for decades, a solitary visit to the deepest place, a brief moment when human eyes looked upon a realm that had been hidden since Earth's oceans formed. Jacques Piccard would go on to design other submersibles and continue his father's work in ocean exploration. He died in 2008, remembered as a pioneer of the deep. Don Walsh continued his Navy career, later becoming a professor and marine policy expert. He never stopped talking about that day in January 1960, when he and Piccard touched the bottom of the world. And the Trieste itself, the bathyscaphe that made the impossible journey, rests now in a museum. The Navy preserved it, recognizing its historical significance. Visitors can see the thick steel sphere. Imagine two men cramped inside for nearly 9 hours, descending through crushing pressure into absolute darkness, trusting their lives to careful engineering and bold ambition. It was a triumph of human ingenuity, a moment when exploration pushed to its absolute limit. And it proved that even the deepest ocean, even the most extreme environment on Earth, could be reached. The Challenger Deep was no longer just a mark on a map, a depth recorded by sonar. It was a place humans had visited, a frontier crossed, a mystery beginning to be understood. That triumph would inspire future generations. It would set the stage for new technologies, new missions, new discoveries in the decades to come. But at that moment, on January 23, 1960, as the Trieste rose to the surface and Piccard and Walsh climbed out into the sunlight, they had accomplished something extraordinary. They had been to the deepest place on Earth and returned to tell the tale. But the story of the Challenger Deep doesn't end with that single heroic dive. Life exists at the bottom, clinging to existence in ways we're only beginning to understand. And the question that naturally follows any first visit is this: what lives down there in the darkness? What creatures have adapted to survive in Earth's most extreme environment? The Challenger Deep lies within what oceanographers call the Hadal Zone, named after Hades, the Greek underworld. This zone extends from 6,000 meters down to the deepest ocean trenches, roughly 11,000 meters. It's the least explored region of the ocean, more mysterious in many ways than the surface of Mars. Only about 6% of the entire ocean exceeds 6,000 meters in depth, and 94% of that Hadal habitat exists in subduction trenches like the Mariana Trench. These are isolated pockets, separated by vast stretches of shallower seafloor. Each trench forms its own distinct ecosystem, sometimes with unique species found nowhere else. Scientists have identified over 400 species living in Hadal zones around the world, and they estimate thousands more remain undiscovered. These creatures have evolved remarkable adaptations to survive where most life cannot. The most obvious challenge is the complete absence of sunlight. On land and in the upper ocean, almost all life depends directly or indirectly on photosynthesis. Plants and algae capture the sun's energy and convert it into sugars, forming the base of the food web. Everything else either eats these primary producers or eats things that eat them. But in the Hadal zone, there's no sunlight, no photosynthesis, no plants or algae growing on the seafloor. So where does the energy come from? The answer is a slow rain from above. Organic particles, the remains of dead organisms from the upper ocean, sink gradually through thousands of meters of water. Scientists call this marine snow, tiny flecks of detritus drifting downward like snowflakes in a midnight sky. Dead plankton, fecal pellets from fish and squid, fragments of larger creatures, bits of seaweed and kelp. This marine snow falls at a rate of about 100 meters per day. From the surface to the Challenger Deep, over 10,000 meters, the journey takes more than 3 months. And most of it gets consumed or decomposed on the way down. Only about 1 to 3% of the organic matter produced at the surface actually reaches the Hadal zone. This means food is incredibly scarce at the bottom. The creatures living there must be efficient scavengers, able to survive on minimal nutrition, patient enough to wait weeks or months between meals. Amphipods are among the most common inhabitants of the Challenger Deep. These are crustaceans, distant cousins of shrimp and crabs, with laterally compressed bodies and no carapace. Most amphipods in shallow water are tiny, just a few millimeters long. But in the Hadal zone, some species display gigantism, growing to extraordinary sizes. The largest confirmed amphipod specimens, collected from depths around 5,300 meters, measured 27 to 28 centimeters long. That's about 11 inches, roughly the size of a small lobster. Reconstructed gut contents from black-footed albatross, seabirds that occasionally catch and eat deep-sea amphipods brought to the surface by currents, suggest specimens up to 34 centimeters. And photographs taken in the Mariana Trench show amphipods that appear to be nearly 35 centimeters in length. Why do Hadal amphipods grow so large? Scientists aren't entirely certain, but several theories exist. The cold temperature and high pressure might favor larger body sizes for metabolic efficiency. Larger animals have a lower surface area to volume ratio, which means they lose heat more slowly and can maintain their internal temperature with less energy expenditure. In an environment where every calorie matters, this could be significant. The scarcity of food might reward size in multiple ways. Larger animals can travel farther in search of meals, covering more ground in their search for the rare food falls from above. They can consume larger pieces of food when they find it, taking bigger bites and storing more energy for the long fasts between meals. Their larger stomachs can hold more food, allowing them to gorge when opportunity strikes. Size also provides advantages in competition. When a food fall arrives, whether it's a dead fish, a whale carcass, or bait deployed by researchers, thousands of amphipods may converge on it. In the feeding frenzy that follows, larger individuals can push smaller ones aside, securing better access to the meal. They can eat faster, consume more, and walk away better nourished. Or it might simply be that predation pressure is lower at extreme depths, allowing creatures to grow without the risk of being eaten. In shallow water, amphipods are prey for many species. Fish, seabirds, seals, and other marine mammals all eat them. Staying small helps them hide, makes them less noticeable, allows them to escape into crevices. But in the Hadal zone, with few predators around, the selective pressure to stay small is reduced. Evolution can favor larger body sizes for other reasons. The phenomenon of deep-sea gigantism appears in other groups too. Giant isopods, cousins of amphipods, can reach over 30 centimeters in length. Giant squid live in deep water. Even some single-celled organisms, like xenophyophores, grow to enormous sizes compared to their shallow water relatives. There's something about the deep ocean that allows or encourages gigantism, though the exact mechanisms remain debated. These amphipods are scavengers, equipped with powerful mandibles that can tear into flesh. When a large food source arrives, like the carcass of a fish or marine mammal, amphipods swarm it in huge numbers, stripping it clean within hours or days. Baited cameras lowered into trenches have recorded thousands of amphipods converging on a single bait package, a writhing mass of pale bodies feeding frantically. They are perfectly adapted to the Hadal environment. Their exoskeletons are flexible, able to withstand pressure. Their metabolism is slow, conserving energy during the long periods between food falls. They reproduce by amplexus, where males grasp females with specialized appendages and guard them for days or weeks until the female is ready to mate. Females carry their eggs in a brood pouch, and the eggs hatch directly into juvenile amphipods with no larval stage, skipping the vulnerable drifting period that most crustaceans go through. But amphipods aren't the only life in the Challenger Deep. Snailfish, members of the family Liparidae, are the most common fish found in Hadal zones. They are strange-looking creatures with tadpole-like bodies, large heads, and gelatinous tissue that gives them a soft, almost translucent appearance. Snailfish hold multiple depth records for fish. In 2014, researchers filmed a snailfish at 8,145 meters in the Mariana Trench. In 2017, another was observed at 8,178 meters. And in 2023, a snailfish was recorded at 8,336 meters in the Izuogasawara Trench near Japan, the deepest fish ever filmed. The deepest described species, meaning one that's been collected and scientifically classified, is Pseudoliparis swirae, found in the Mariana Trench at depths down to 8,076 meters. This species is pale pink, eyeless, and about 10 centimeters long. It represents the extreme limit of what fish can achieve. Scientists believe there's a hard biochemical limit to how deep fish can live, somewhere between 8,000 and 8,500 meters. Beyond that depth, the pressure makes it impossible for their body chemistry to function. The issue is osmotic pressure. Fish need to maintain a certain salt concentration in their cells and body fluids to keep proteins working correctly. But at extreme depths, the external pressure is so high that it would force water out of their cells unless they compensate somehow. To counteract this, Hadal fish accumulate a compound called trimethylamine N-oxide, or TMAO, in their tissues. TMAO stabilizes proteins under pressure and helps maintain osmotic balance. Pseudoliparis swirae has the highest TMAO concentration ever measured in a fish. But there's a limit. Beyond 8,000 to 8,500 meters, the amount of TMAO needed would make the fish's tissues hyperosmotic, meaning too salty to function. The fish would essentially be too salty to live. This creates a biochemical barrier that vertebrates simply cannot cross. So if you descend to the very bottom of the Challenger Deep, to 10,900 meters, you won't find fish. It's too deep. The few fish that live in Hadal zones stay in the upper reaches, between 6,000 and 8,000 meters. Deeper than that, you find only invertebrates, amphipods, sea cucumbers, strange worm-like creatures, and microscopic life. Snailfish that do live at Hadal depths have evolved remarkable adaptations. Their bodies are mostly water and gelatinous tissue, with very little protein, lipid, or carbohydrate. This reduces their metabolic needs and makes them neutrally buoyant, requiring less energy to move. Their muscles are weak and watery, but they don't need powerful muscles in an environment where nothing moves quickly. They've lost their eyes. There's no point in having eyes where there's no light. Genetic analysis shows that genes for color vision and pigmentation have been deleted or rendered non-functional. Hadal snailfish are colorless and blind, navigating by touch and chemical sensing. Their skeletons are cartilage rather than bone, and even that cartilage is flexible and poorly calcified. This allows their bodies to withstand pressure without rigid structures that might crack or shatter. Their skulls are incomplete, with gaps that allow tissue to bulge outward. It looks strange to us, but it works perfectly in their environment. They have no swim bladders, the gas-filled organs that most fish use for buoyancy control. A swim bladder would be useless at Hadal depths, where gas is compressed to tiny volumes. Instead, Hadal snailfish use their low-density tissues for buoyancy, floating effortlessly through the water. Interestingly, larval snailfish may spend time near the surface. Some species release eggs that drift upward into shallower water, where the larvae hatch and spend their early life feeding on plankton in the more productive upper ocean. Then, as they mature, they migrate downward to the depths where adults live. This allows them to take advantage of the abundant food near the surface during their growth phase, even though they'll spend most of their lives in the food-scarce deep. The snailfish diet consists mainly of amphipods and small crustaceans. They are predators, but slow and patient ones, drifting through the water until they encounter prey, then lunging with surprising speed to capture it. Their mouths are large relative to their body size, allowing them to swallow prey nearly as big as themselves. Beyond amphipods and snailfish, other creatures inhabit the Hadal zone. Sea cucumbers, which look like soft sausages lying on the seafloor, crawl slowly across the sediment, consuming organic particles. Some species can be quite large, 30 or 40 centimeters long, dominating the landscape in underwater photographs. Xenophyrophores are among the strangest inhabitants. These are single-celled organisms, but they can grow to over 10 centimeters in diameter, making them the largest known single-celled creatures on Earth. They build delicate, branching structures from sediment particles glued together with a secreted cement. These structures provide habitat for smaller organisms and play a role in sediment mixing. Polychaete worms burrow through the sediment, some with feathery appendages that filter food from the water. Isopods, crustaceans related to pill bugs, scuttle across the bottom on multiple legs. Small snails and clams have been found, though they are rare at the greatest depths. There are also bacteria, of course. Microorganisms are everywhere in the ocean, even at 11,000 meters. They break down organic matter, recycle nutrients, and form the base of the food web. Some are chemosynthetic, meaning they derive energy from chemical reactions rather than sunlight, using compounds like hydrogen sulfide or methane as their energy source. These bacteria can support small ecosystems around hydrothermal vents or cold seeps, though such features are rare in the deepest trenches. The total biomass at Hadal depths is extremely low. There simply isn't enough food to support large populations. But the diversity is surprising. Scientists who study Hadal ecosystems are continually amazed by the variety of life that manages to exist under such extreme conditions. And life at these depths faces challenges beyond just pressure and darkness. The water moves very slowly, so oxygen replenishment is limited. Dissolved oxygen concentrations can be lower than in shallower water, creating an additional stress for organisms that need to extract oxygen for respiration. The sediment is soft and unstable, making it difficult for organisms to anchor themselves or build permanent structures. Most creatures are mobile, able to move in search of food, or they burrow into the sediment for protection. Reproduction is challenging. Populations are sparse, so finding a mate can be difficult. Many Hadal species have evolved strategies to increase their chances, like chemical signaling that allows individuals to locate each other over long distances, or hermaphroditism, where individuals possess both male and female reproductive organs and can mate with any other individual they encounter. Some species practice brood care, with parents protecting eggs or young to increase survival rates. Others produce large numbers of eggs, relying on sheer quantity to ensure that at least some offspring survive. The creatures of the Challenger Deep are survivors in the truest sense. They live in a place that seems designed to exclude life, yet they persist. They've evolved solutions to problems that would be insurmountable for most organisms. And they remind us that life is remarkably resilient, capable of adapting to almost any environment Earth can create. The adaptations that allow organisms to survive in the Hadal zone are marvels of evolution, biochemical and physical solutions to extreme challenges. Understanding these adaptations gives us insight not only into how life works on Earth, but also into how it might exist elsewhere in the universe, on worlds with extreme environments. The single most important adaptation is pressure tolerance. At the bottom of the Challenger Deep, the pressure is over 1,000 times greater than at sea level. This pressure affects every aspect of biology, from the structure of proteins to the fluidity of cell membranes. Proteins, the molecular machines that do most of the work in cells, are three-dimensional structures held together by weak chemical bonds. Pressure can distort these structures, causing them to unfold or misfold, losing their function. For most surface organisms, the pressure at Hadal depths would destroy their proteins, killing their cells. Hadal organisms have evolved modified proteins with altered structures that remain stable under pressure. The key is in the arrangement of amino acids, the building blocks of proteins. Hadal fish and invertebrates have proteins with fewer cavities and more compact folding, reducing the areas where pressure can cause distortion. They also accumulate high concentrations of trimethylamine N-oxide, or TMAO, that compound mentioned earlier. TMAO is a small molecule that acts as a pressure protectant. It stabilizes protein structures, helping them maintain their shape even under crushing force. The deeper the organism lives, the higher its TMAO concentration needs to be. Pseudoliparis swirae, the deepest living described fish, has TMAO concentrations higher than any other known vertebrate. Its cells are essentially soaked in this protective compound, allowing its proteins to function at 8,000 meters depth. But TMAO isn't without cost. At high concentrations, it makes cells hyperosmotic, meaning they have a higher salt concentration than the surrounding water. This tends to draw water into cells, which could cause them to swell and burst. To counteract this, Hadal organisms must carefully balance their internal chemistry, a delicate act that becomes impossible beyond a certain depth. This is why scientists believe 8,000 to 8,500 meters is the maximum depth for fish. Beyond that, the TMAO concentration needed for pressure protection would make their cells too salty to function. It's a hard limit imposed by chemistry, not something evolution can overcome. Cell membranes, the thin barriers that surround every cell, also face challenges from pressure. Membranes are made of lipids, fatty molecules arranged in a double layer. At high pressure, these lipids pack more tightly together, making the membrane more rigid and less functional. Hadal organisms compensate by altering the types of lipids in their membranes. They use lipids with more unsaturated fatty acids, which have kinks in their molecular structure that prevent tight packing. This keeps membranes fluid and functional even under extreme pressure. Some deep-sea creatures also increase the amount of cholesterol in their membranes, which helps maintain the right balance of fluidity and stability. It's a complex chemical juggling act, fine-tuned over millions of years of evolution. Hadal fish have largely lost their bones. Bones are made of calcium phosphate, a hard mineral that provides structure and support. In shallow water fish, bones are essential. They support the body against gravity and water resistance, provide attachment points for muscles, protect vital organs, and store minerals. But at extreme pressure, hard rigid structures become a liability. They can crack or shatter under stress. The calcium phosphate crystals that make bones hard are compressed differently than the surrounding tissue, creating stress points where fractures can occur. Hadal fish have evolved cartilaginous skeletons instead, flexible and able to deform without breaking. Cartilage is softer than bone, made mostly of collagen and other proteins with little mineralization. It bends rather than snaps. In Hadal fish, even this cartilage is poorly calcified, remaining soft and pliable throughout their lives. Genetic studies of Pseudoliparis suaire revealed something fascinating. They found mutations in the gene responsible for cartilage calcification, specifically a gene called BGLAP, which codes for a protein that helps deposit calcium in cartilage. Without this gene functioning normally, their cartilage remains soft and flexible, unable to mineralize properly. This would be a serious deficiency in shallow water fish, causing skeletal deformities and weakness. But in the Hadal zone, it's an advantage, allowing their skeletons to withstand extreme pressure without the brittleness that mineralized bone would bring. Their skulls tell the story most dramatically. Where shallow water fish have closed, rigid skull cases protecting their brains, Hadal snailfish have incomplete skulls with large gaps where bone would normally form. These fontanelles, similar to the soft spots in human infant skulls, never close. This gives their tissues room to expand or compress in response to pressure changes without causing damage. Their brains aren't enclosed in rigid bone, they are cushioned by fluid and soft tissue that can adjust to changing conditions. They look strange compared to shallow water fish, with bulging foreheads and soft, pliable heads that seem almost deformed. If you could touch one, the head would feel soft, almost squishy, nothing like the hard skull of a typical fish. But form follows function, and their form is perfectly adapted to their environment. What looks like a deficiency is actually a sophisticated adaptation. The loss of eyesight in Hadal fish is another striking adaptation. Eyes are metabolically expensive to build and maintain. In an environment with no light, they serve no purpose. Evolution has eliminated them, redirecting that energy to other systems. Genetic analysis shows that multiple genes related to vision have been lost or rendered non-functional in Hadal snailfish. Genes for color vision, for pigmentation, even for the basic structure of the eye itself have been deleted or mutated. The result is a fish that's essentially blind, navigating by other senses. Instead of vision, Hadal fish rely heavily on their lateral line system, a series of sensory organs that detect vibrations and pressure changes in the water. They can sense the movement of prey or predators, the presence of obstacles, even the subtle currents caused by other organisms. It's a different way of perceiving the world, one that doesn't require light. Their skin is also covered with chemical receptors, allowing them to taste the water around them. They can detect the chemical signature of food or potential mates, following gradients of concentration to their source. In some ways, they smell and taste their way through the darkness, building a chemical map of their surroundings. Metabolism in Hadal organisms is generally slow. With food scarce and energy at a premium, there's no advantage to rapid movement or quick reactions. Most Hadal creatures are sluggish by surface standards, moving in slow motion, conserving every calorie. Their muscles are weak and watery, composed largely of water with minimal protein. This reduces their metabolic cost but also limits their strength and speed. They can't swim fast or fight vigorously. But they don't need to. There are few predators at Hadal depths, and prey doesn't move quickly either. Some Hadal organisms can survive weeks or even months without food. They enter a state of metabolic dormancy, reducing their energy consumption to the bare minimum needed to stay alive. When food arrives, in the form of a carcass or a food fall from above, they rouse themselves to feed, storing as much energy as possible before the next long fast. Reproduction in the Hadal zone presents unique challenges. Populations are sparse, spread thinly across vast areas. Finding a mate in the darkness can be nearly impossible. Many species have evolved strategies to increase their chances. Some use bioluminescence, chemical light produced by their own bodies, to signal potential mates. These flashes are brief and dim, but in complete darkness, they stand out. Each species has its own flashing pattern, a kind of Morse code that announces identity and readiness to mate. Others release chemical signals called pheromones into the water. These compounds can drift long distances, creating a trail that other individuals can follow. When a male detects a female's pheromone, he swims toward the source, potentially traveling hundreds of meters through the darkness. Some species are hermaphroditic, possessing both male and female reproductive organs. This doubles their chances of successful reproduction, since any two individuals that meet can potentially mate. It's an efficient solution when encounters are rare. Amphipods practice amplexus, a behavior where males grasp females with specialized appendages and hold on for days or weeks. The male waits patiently until the female molts and is ready to mate, then fertilizes her eggs immediately. This ensures that he's in the right place at the right time, eliminating the need to search for a mate when the critical moment arrives. Females often produce large eggs with substantial yolk reserves, giving their offspring a better chance of survival. Instead of releasing thousands of tiny eggs that drift in the plankton, Hadal species produce fewer, larger eggs that are better provisioned. Quality over quantity. Some species lack larval stages entirely. The eggs hatch directly into miniature versions of the adults, skipping the vulnerable drifting phase that most marine organisms go through. This is unusual in the ocean, where most creatures start life as tiny larvae that float in the plankton for weeks or months. But in the Hadal zone, where currents are weak and food for larvae is scarce, direct development makes sense. Bioluminescence, the production of light by living organisms, is common in the deep ocean but less so in Hadal zones. The chemistry of bioluminescence requires energy, and at the greatest depths, that energy is better spent on survival than on producing light. However, some Hadal organisms do bioluminesce, particularly those living in the upper reaches of Hadal zones around 6,000 to 7,000 meters. They use it for camouflage, a technique called counterillumination. By producing light on their underside that matches the faint glow from above, they erase their silhouette, making themselves invisible to predators looking up from below. Others use bioluminescence to startle predators. When threatened, they emit a bright flash of light, momentarily blinding or confusing the attacker, giving them a chance to escape. It's the deep-sea equivalent of a flashbang grenade. The food web in the Hadal zone is relatively simple compared to shallow ecosystems, but it's far from simplistic. At the base are bacteria and other microorganisms that break down organic matter, releasing nutrients back into the water. These microbes are everywhere, colonizing every surface, living in the sediment, suspended in the water column. They're the true foundation of Hadal life. These bacteria include both aerobic species that use oxygen for respiration and anaerobic species that can function without it. Some are chemosynthetic, deriving energy from chemical reactions involving sulfur, methane, or other compounds rather than relying entirely on organic matter from above. Near hydrothermal vents or cold seeps, where chemicals leak from the seafloor, these chemosynthetic bacteria can form dense mats, supporting small oases of life independent of surface productivity. The bacteria are consumed by small invertebrates like nematode worms, microscopic crustaceans, and protozoans. These tiny grazers and filter feeders process vast quantities of water and sediment, extracting bacteria and organic particles. Though individually tiny, their collective impact is substantial, cycling nutrients and energy through the ecosystem. Larger invertebrates, particularly amphipods, occupy the next level. They are omnivorous scavengers, eating anything they can find: dead organisms, fecal pellets, marine snow, bacteria, and even each other when food is scarce. When a large food fall arrives, like a fish carcass or piece of wood, they swarm it in huge numbers. Baited cameras placed on the Hadal floor have recorded swarms of hundreds or thousands of amphipods converging on bait within hours. The feeding frenzy is intense. Amphipods tear at the food with their powerful mandibles, ripping off chunks and consuming them rapidly. They eat until their bodies are distended, visibly swollen with food. Then they retreat into the darkness to digest, their metabolism processing the meal over days or weeks. A single large food fall can sustain a population of amphipods for months. Snailfish prey mainly on amphipods and other small crustaceans. They are ambush predators, hovering motionless in the water until prey comes within range, then lunging with surprising speed. Their large mouths can engulf prey nearly as big as themselves, swallowing amphipods whole. They may eat only a few times per month, their slow metabolism allowing them to survive on infrequent meals. At the top are scavengers that can eat anything, from carcasses to each other. Sea cucumbers plow through sediment, extracting any organic matter. Polychaete worms burrow and hunt through the sediment layers. The system has few true predators in the traditional sense. Most organisms are opportunistic, eating whatever they encounter. They are consumed by small invertebrates like amphipods, which are in turn eaten by larger predators like snailfish. At the top are scavengers that can eat anything, from carcasses to each other. There's very little primary production at Hadal depths. A few chemosynthetic bacteria derive energy from chemicals, but they contribute minimally to the overall food supply. The vast majority of energy comes from marine snow, the steady rain of organic particles from the sunlit surface waters thousands of meters above. This makes Hadal ecosystems dependent on the productivity of the surface ocean. When surface waters are rich with life, more organic matter sinks to the depths, and Hadal populations can thrive. When surface productivity declines, perhaps due to climate change or ocean acidification, the Hadal zone suffers as well. The two are connected by that slow, steady rain of detritus. One of the most surprising discoveries about Hadal life is its diversity. Each trench system tends to have unique species found nowhere else. The Mariana Trench has its own set of creatures, distinct from those in the Kermadec Trench or the Peru-Chile Trench. These trenches are isolated from each other by thousands of kilometers of shallower seafloor, creating what scientists call habitat islands. Over millions of years, populations in different trenches have evolved independently, diverging into separate species. This has created a patchwork of biodiversity scattered across the Hadal zone, with each trench harboring its own unique assemblage of life. It also means that many Hadal species have very limited ranges. They exist in a single trench system and nowhere else on Earth. This makes them vulnerable to disturbance. If something damages their trench, like deep-sea mining or pollution, the entire species could be lost. The adaptations of Hadal organisms represent millions of years of evolution fine-tuning life to survive at the extremes. They show us the remarkable plasticity of biology, the ability of natural selection to find solutions to seemingly impossible problems. And they raise intriguing questions about life beyond Earth. If life can exist at the bottom of the Challenger Deep, under crushing pressure and complete darkness, could it exist in the subsurface oceans of Europa or Enceladus, moons of Jupiter and Saturn that harbor liquid water beneath thick ice shells? Could it exist on planets with extreme gravity or in the crushing atmospheres of gas giants? The creatures of the Hadal zone expand our understanding of what's possible. They show that life is not fragile or limited to narrow conditions. It's adaptable, resilient, and capable of thriving in places we once thought uninhabitable. Every discovery in the deep ocean opens new possibilities for where we might find life elsewhere in the universe. After the Trieste's historic dive in 1960, the Challenger Deep went unvisited by humans for over half a century. The technology existed to go deeper, but the cost and risk were enormous, and scientific priorities shifted to other frontiers. The deep ocean remained largely unexplored, a frontier ignored. But in the early 2000s, a new generation of explorers began looking downward again. Advances in materials science, robotics, and engineering made deep-diving submersibles more feasible. And one man in particular became obsessed with reaching the Challenger Deep. James Cameron, the filmmaker behind movies like Titanic and Avatar, had been fascinated by the ocean since childhood. He'd made multiple dives to the wreck of the Titanic and directed documentaries about deep-sea exploration. But he wanted to go deeper, to reach the ultimate depth. In 2005, Cameron began working with Australian engineer Ron Allum to design a new submersible specifically for diving to the Challenger Deep. They called it Deep Sea Challenger, and it would incorporate technologies far advanced from the Trieste's 1950s design. The project took 7 years. Cameron and Allum worked with a team at Acheron Project Party Limited in Sydney, building the submersible in a workshop in Leichhardt, a suburb of Sydney. They partnered with the National Geographic Society for funding and documentation, and received support from Rolex, the Swiss watchmaker that had a long history of deep-sea exploration equipment. The design philosophy was radically different from the Trieste. Instead of a large gasoline float with a cruise sphere dangling beneath, Deep Sea Challenger would be a vertical torpedo, a single integrated vehicle that descended nose-first into the depths. The key innovation was a material called ISOFLOAT syntactic foam. This was a type of composite material made from millions of hollow glass microspheres suspended in an epoxy resin matrix. The glass spheres provided buoyancy without compressing under pressure, and the overall density of the foam was about 0.7, meaning it floated in water. Ron Allum developed a specific formulation of syntactic foam for the submersible, creating a material that was more homogeneous and reliable than commercial syntactic foams. This ISOFLOAT foam comprised about 70% of the submersible's volume, providing enough buoyancy to bring the vehicle to the surface even if all other systems failed. The foam surrounded a vertical pressure sphere made of 64 mm thick steel. Unlike the Trieste spherical design, which accommodated 2 people, Deep Sea Challenger's sphere was just large enough for one person sitting in a semi-recumbent position. Cameron would pilot it alone, the first solo dive to the Challenger Deep. The sphere was tested at Penn State University's Applied Research Laboratory, where it was subjected to pressures equivalent to 16,500 pounds per square inch, or 114 megapascals. That's higher than the pressure at the Challenger Deep, providing a safety margin. The sphere passed all tests without deformation or failure. The entire submersible was 7.3 meters long when oriented vertically, its operating configuration. It weighed 11.8 metric tons, but its weight in water was much less due to the buoyant foam. 10 metric tons of steel ballast weights attached to the bottom provided the negative buoyancy needed for descent. To ascend, these weights would be jettisoned, and the foam would pull the submersible upward. The vehicle incorporated over 180 separate systems, each one critical to the mission. These included life support, navigation, communication, lighting, cameras, and scientific sampling equipment. A programmable logic controller from Opto22, a company based in Temecula, California, monitored all systems, recording depth, heading, temperature, pressure, and battery status every 3 minutes. Power came from lithium battery packs, chosen for their high energy density. LED lighting arrays, 10 panels producing 20,000 lumens each, could illuminate the seafloor with brilliant white light, something the Trieste could never achieve with its incandescent bulbs. 3D camera systems were mounted on the front, designed to capture stereoscopic footage of the deep ocean. This was Cameron's specialty, merging his filmmaking expertise with exploration. He wanted to bring back images that would immerse viewers in the experience of being at the bottom of the world. Communication with the surface relied on an underwater acoustic system from L3 Nautronics, based in West Australia. Sound waves transmitted data and voice, allowing Cameron to talk to the support ship even from 11 kilometers below. The communication was one way at a time, with delays, but it worked reliably. Propulsion came from multiple electric thrusters, allowing the submersible to maneuver horizontally and adjust its depth precisely. A ballast system could be fine-tuned by pumping water in or out of tanks, trimming the vehicle to neutral buoyancy. Safety was paramount. Multiple redundant systems ensured that even if several failures occurred, the submersible could still return to the surface. The ballast weights were attached with galvanic releases, metal components designed to corrode in seawater. If power failed completely and Cameron couldn't manually release the weights, they would eventually corrode and fall off on their own, allowing the submersible to ascend automatically. It might take hours or days, but it would happen. The submersible underwent extensive testing before attempting the Challenger Deep. In late January 2012, it was deployed in Sydney's naval yards for surface tests, checking systems and making adjustments. On February 21st, the first deep test dive was attempted, targeting 1,000 meters. But problems with cameras and life support systems forced an abort. The submersible was brought back to the surface for repairs. On February 23rd, another attempt reached 991 meters off New Britain Island in Papua New Guinea. Cameron rendezvoused with a remotely operated vehicle at depth, demonstrating that the submersible could work alongside other vehicles. On February 28th, a dive reached 3,700 meters, staying down for 7 hours. During this dive, power fluctuations occurred, but systems remained stable. Cameron collected biological samples and tested the scientific equipment. On March 4th, a dive targeted the New Britain Trench, aiming for over 7,000 meters. Issues with a vertical thruster limited maximum depth, but the dive proved that the submersible could handle deep pressure. Later in March, another dive successfully reached the bottom of the New Britain Trench at 8,221 meters. Cameron spent time on the seafloor, observing a sediment plain dotted with anemones and jellyfish. He collected samples and took extensive footage. It was the deepest anyone had gone since the Trieste, and it proved Deep Sea Challenger was ready for the ultimate challenge. The submersible was transported to Guam and loaded aboard the support ship Mermaid Sapphire. They departed Ulithi Atoll, heading for the Challenger Deep. The weather was monitored carefully. They needed calm seas for the launch, since deploying the vehicle in rough conditions could damage it or risk the pilot's life. On March 26, 2012, conditions were favorable. The sea was relatively calm, the winds manageable. Deep Sea Challenger was lowered into the water by a large A-frame crane. Cameron climbed inside through the narrow hatch, and the hatch was sealed from outside. The submersible's computers ran through final checks. All systems showed green. Cameron activated the ballast system, and Deep Sea Challenger began to sink. The descent was faster than the Trieste's, thanks to the streamlined design and heavier ballast. Cameron dropped through the water column at a steady rate, passing through the twilight zone into complete darkness within minutes. He descended vertically, nose pointed down, encased in the steel sphere with instruments surrounding him. The temperature inside dropped as heat conducted away through the hull. He wore multiple layers of clothing to stay warm, but the cold was manageable. Through the small acrylic viewport, he could see nothing but blackness. The LED lights illuminated particles in the water, marine snow drifting past, but there was nothing else to see. Just darkness and the occasional flash of bioluminescence from startled organisms. The descent took 2 hours and 37 minutes, nearly twice as fast as the Trieste 4 hours and 47 minutes. Modern materials and design made all the difference. At around 10,800 meters, Cameron felt a gentle shudder. Deep Sea Challenger had touched the bottom. He checked the depth gauge, 10,908 meters. He'd reached the Challenger deep, becoming the third person to visit this place, and the first to go solo. He adjusted the ballast to settle gently on the sediment, then released a marker, a steel weight that would remain on the bottom, documenting the dive. Through the viewport and on the external cameras, he could see the seafloor. It looked like a barren desert, a pale expanse of fine sediment stretching away into darkness. The LED lights illuminated a circle perhaps 10 meters across, beyond which everything faded into black. No plants, no corals, no large structures. Just flat, featureless ooze. But there was life. Small organisms moved across the sediment, possibly amphipods or sea cucumbers. Particles drifted in the water, some of them likely living creatures too small to see clearly. Cameron maneuvered the submersible slowly, collecting samples with a robotic arm. He'd planned to spend 6 hours on the bottom, conducting extensive exploration and filming. But problems arose. The hydraulic system that powered the sampling equipment began to leak, limiting its function. Worse, the sonar system failed, making it difficult to navigate. Without sonar, he couldn't map his surroundings or locate the landers that had been deployed earlier to collect biological samples. He made the decision to cut the dive short. He'd proven he could reach the bottom, had collected some samples, and filmed the environment. Staying longer with failing systems risked the mission. After 3 hours on the seafloor, much less than planned but still longer than any previous dive, he jettisoned the ballast weights. Deep Sea Challenger rose rapidly, pulled upward by the buoyant syntactic foam. The ascent was uneventful, a steady climb through the darkness back toward the surface. Cameron monitored systems, reviewed footage, and reflected on what he'd accomplished. After 3 hours and 57 minutes of ascent, the submersible broke through the surface. Cameron had returned safely. The mission was a success, despite the technical issues that cut it short. He'd taken Deep Sea Challenger to a depth of 10,908 meters at the moment of touchdown, with a maximum depth of 10,898 meters recorded during the descent. Slightly less deep than the Trieste measurement, but within the margin of error given the difficulty of precisely locating the deepest spot. Cameron's dive was historic for several reasons. He was the first person to make a solo descent to the Challenger deep, relying entirely on his own skills without a co-pilot. He spent more time on the bottom than Pickard and Walsh, 3 hours compared to their 20 minutes. And he brought back high-definition footage, giving the world its first clear look at the deepest place on Earth. The footage showed a stark, alien landscape. The sediment was disturbed by his submersible's landing, puffing up in clouds. Small organisms darted away from the lights. The water was crystal clear, devoid of the particles and plankton that cloud shallower waters. It was a world of profound silence and stillness, a place where time seemed irrelevant. Scientists analyzed the samples Cameron collected, finding bacteria, amphipods, and organic material. The biological data confirmed what the Trieste dive had suggested. Life exists at the bottom of the Challenger deep, sparse but persistent. On March 26, 2013, exactly 1 year after the dive, Cameron donated Deep Sea Challenger to the Woods Hole Oceanographic Institution, one of the world's leading ocean research centers. He wanted the submersible to be used for science, not just to sit in a museum. But fate had other plans. On July 23, 2015, while being transported to Connecticut for an exhibit, the truck carrying Deep Sea Challenger caught fire on Interstate 95. The truck's brakes failed, causing the tires to ignite. The fire damaged the submersible significantly, though the pressure sphere itself survived. The vehicle was moved to California for repairs in February 2016, but restoration was slow and expensive. Eventually, Deep Sea Challenger was exhibited at the Natural History Museum of Los Angeles County from December 2022 to February 2023, then moved to the Royal Canadian Geographical Society in Ottawa, where it remained through November 2023. The submersible may never dive again. The cost to fully repair and recertify it is enormous. But it served its purpose. It proved that solo dives to the Challenger Deep were possible. It brought back footage and samples that advanced our understanding. And it inspired a new generation to look toward the ocean's depths as a frontier worth exploring. James Cameron's dive reignited interest in deep ocean exploration. It showed that modern technology could reach places thought unreachable. And it set the stage for what would come next. Not just solo expeditions, but multiple dives, multiple explorers, and the beginning of regular access to the deepest ocean. The age of Hadal exploration had truly begun, moving from rare heroic expeditions to systematic scientific investigation. And the next chapter would be written by a man who wouldn't just visit the Challenger Deep once or twice, but over and over, bringing others with him, opening the deep ocean to more people than ever before. The newest era of deep ocean exploration began with a submersible unlike any before it. DSV limiting factor, also known as Triton 36002, was designed from the outset for repeated dives to the deepest places on Earth. Where the Trieste made one dive and Deep Sea Challenger made one, limiting factor was built for dozens, eventually hundreds of dives. The submersible was manufactured by Triton Submarines, a company based in Florida that specializes in deep diving vehicles. The client was Victor Vescovo, a private equity investor and former Navy Reserve intelligence officer who had already achieved the Explorer's Grand Slam, climbing the highest peak on each continent and skiing to both poles. But Vescovo wanted more. He wanted to dive to the deepest point in each of the world's 5 oceans: the Atlantic, Pacific, Indian, Southern, and Arctic. He called it the 5 Deeps Expedition, and he commissioned Triton to build a submersible that could take him there. The result was DSV limiting factor, and its design represented the cutting edge of deep submergence technology. The pressure hull was made of titanium, specifically grade 5 titanium alloy, also known as T604VELI. This alloy contains 6% aluminum and 4% vanadium, with extra-low interstitials for improved toughness. The hull was a sphere 1,500 mm in inside diameter with walls 90 mm thick. It was machined to extraordinary precision, 99.933% spherical. This near-perfect geometry was critical for distributing pressure evenly, preventing stress concentrations that could cause failure. The sphere was built in 3 main pieces, an equatorial ring and 2 forged titanium dome caps. These pieces were sealed together with O-rings and precision-machined flanges. The entire assembly was certified by DNV, a classification society that set standards for marine vessels, to 11,000 meters depth. But it was tested to 14,000 meters seawater, or 4,000 to 6,000 feet seawater, equivalent to 1,400 bar or 20,000 pounds per square inch. That's significantly deeper than the Challenger Deep, providing a safety margin. The submersible's mass was 12,500 kilograms, and it could accommodate a pilot plus one observer. Endurance was 16 hours of normal operation, with 9 to 6 hours of emergency life support if needed. The crew could survive for 4 days even if all active systems failed. Syntactic foam provided buoyancy, similar to Deep-Sea Challenger but in modular blocks attached around the pressure sphere. 500 kilograms of ballast weights plus 100 kilograms of trim weights could be jettisoned for ascent. As a backup, the weights were also connected by galvanic releases that would corrode in seawater, allowing automatic ascent even if power failed. Propulsion came from 10 ducted thrusters, 4 horizontal, 4 vertical, and 2 maneuvering thrusters that could be jettisoned if they became fouled. This gave the submersible excellent maneuverability, allowing it to hover in place or move in any direction. A manipulator arm, the Craft Telerobotics Raptor with 7 functions and force feedback, allowed the pilot to collect samples, deploy instruments, or interact with the environment. The arm was strong enough to lift heavy objects yet precise enough to handle delicate specimens. 3 ultra-wide-angle acrylic viewports provided unobstructed views in multiple directions. 10 LED lighting panels, each producing 20,000 lumens, could illuminate the seafloor like daylight. 4 full ocean depth low-light cameras and 4 HD mission cameras recorded everything, inside and out. The pilot controlled the submersible with joysticks, touchscreen interfaces, and manual backup controls. Temperature and humidity were regulated. Carbon dioxide scrubbers removed exhaled CO2, and oxygen was replenished from tanks. Even if the electronics failed, the crew could breathe for days. Launch and recovery used a hydraulic A-frame on the support vessel, lifting the submersible in and out of the water. In rough seas, this was the most dangerous part of the operation, but the system was robust and well-designed. Victor Vescovo trained extensively to pilot the submersible. Unlike Cameron, who was a filmmaker first, Vescovo had a military background and experience with complex systems. He approached deep diving with meticulous planning and risk management. The 5 Deeps expedition began in earnest in late 2018. The support vessel, a former oil survey ship named Pressure Drop, was refurbished specifically for the mission. It carried the submersible, a team of scientists and engineers, and all the equipment needed for deep ocean operations. In December 2018, Vescovo dived to the Puerto Rico Trench, the deepest point in the Atlantic Ocean, reaching 8,376 meters in a place called the Brownson Deep. It was the first ever crewed dive to the Atlantic's deepest point. On February 4, 2019, he dived to the bottom of the South Sandwich Trench in the Southern Ocean, again the first ever crewed visit to that ocean's deepest point. On April 16, 2019, he reached the Sunda Trench south of Bali, Indonesia, the deepest point in the Indian Ocean. During this dive, he observed Hadal snailfish and stalked ascidians, documenting life at extreme depths. But the big challenge remained: the Challenger Deep in the Mariana Trench, the deepest point in the Pacific and on Earth. On April 28, 2019, Victor Vescovo piloted DSV limiting factor to the bottom of the Challenger Deep. The initial depth measurement from the submersible's instruments showed 10,928 meters, a new world record by 16 meters. But depth measurements at such extremes are complex. They depend on the speed of sound in water, which varies with temperature, salinity, and pressure. After the dive, scientists post-processed the data using readings from acoustic altimeters, in situ pressure sensors, and measurements from robotic landers deployed alongside the submersible. The corrected depth was 10,935 meters, plus or minus 6 meters. The coordinates were 11 degrees, 22.3 minutes north latitude, and 142 degrees, 35.3 minutes east longitude. This became the new recognized deepest point in Earth's oceans, surpassing all previous measurements. 3 days later, on May 1st, Vescovo dived again. He became the first person to dive to the Challenger Deep twice, a feat that would have seemed impossible just a few years earlier. During this dive, he made discoveries that were both exciting and sobering. He found at least 3 new species, organisms never before seen by science. These would need to be collected and studied to be formally described, but their presence confirmed that Hadal biodiversity was greater than expected. He also found plastic. A plastic bag and candy wrappers lying on the sediment at the deepest point in the ocean. Humans had reached the most remote place on Earth, and our waste had reached it too. It was a stark reminder that no part of the planet remains untouched by human activity. During the dive, Vescovo encountered a Hadal snailfish at approximately 8,000 meters depth, and a spoonworm, a type of marine invertebrate, at around 7,000 meters. The spoonworm sighting was particularly significant because it was the deepest ever recorded for that species. On May 7th, Vescovo and Dr. Alan Jameson, a leading expert on Hadal zone biology from Newcastle University, dived to the Serena Deep, the third deepest location in the Mariana Trench, about 128 miles northeast of the Challenger Deep. They spent 176 minutes on the bottom, collecting samples of mantle rock from the western slope of the trench. This rock provided insights into the geological processes driving subduction. The 5 Deeps expedition continued. On June 10, 2019, Vescovo dived to the Horizon Deep in the Tonga Trench, reaching 10,823 meters. This confirmed the Tonga Trench as the second deepest location in the world, and the deepest in the southern hemisphere. The site was completely pristine, with no evidence of human contamination. On August 24, 2019, Vescovo completed the 5 Deeps by diving to the Molloy Deep in the Arctic Ocean, reaching 5,550 meters. It was the first ever crewed dive to this location. But Vescovo wasn't done with the Challenger Deep. He returned in June 2020, conducting a series of dives that brought other people to the deepest point. Over several days, he piloted the submersible with different observers, sharing the experience of reaching the bottom of the world. One of those passengers was Kelly Walsh, the son of Don Walsh, the Navy lieutenant who had dived with Jacques Piccard in 1960. Kelly Walsh became the 11th person to reach the Challenger Deep, and he and his father became the only father-son team to have made the journey 60 years apart. It was a deeply emotional moment, connecting the first dive to the modern era. Another passenger was Catherine Sullivan, a former astronaut and NOAA administrator. By reaching the Challenger Deep, she became the first woman to reach the deepest point in the ocean. She also became the first person to have been both to space and to the deepest ocean, a unique achievement spanning the extremes of human exploration. Vanessa O'Brien, an explorer and mountaineer, also dived with Vescovo. She became the first woman to have both climbed Mount Everest and descended to the Challenger Deep, another unique combination of achievements. By the end of 2022, Victor Vescovo had made 15 total dives to the Challenger Deep, more than anyone else in history. He held the record for the deepest dive, and he demonstrated that regular access to the Hadal zone was now possible. Over 21 people total have now visited the Challenger Deep, a number that would have seemed unimaginable in 1960. The deep ocean is no longer the exclusive domain of government-funded expeditions with decades between attempts. It's becoming accessible, at least to those with the resources and determination to get there. In 2022, Vescovo sold DSV limiting factor and the support vessel pressure drop to Inkfish, an ocean exploration organization owned by Gabe Newell, the co-founder of Valve Corporation. The sale included the submersible, all support equipment, and the Kongsberg EM-124 multibeam echo sounder used for seafloor mapping. Under Inkfish's ownership, the submersible was renamed Bakunawa, after a creature from Filipino mythology. The support vessel was renamed Dagon, after a Mesopotamian deity. Professor Alan Jameson, who had moved to the University of Western Australia, became the chief scientist for the ongoing expedition program. Inkfish plans to continue exploring the Hadal Zone, conducting scientific research, and potentially offering opportunities for others to visit the deep ocean. The exact details are still developing, but the intent is clear: to make deep ocean exploration ongoing and systematic rather than sporadic and rare. On April 16, 2024, pilot Kate Wawatai and marine geologist Dr. Heather Stewart conducted the first all-woman dive to 8,000 meters, reaching the Novacanton Trough in the Clarion-Clipperton Zone. The dive lasted 10 hours and included studies of how fracture zones act as pathways for deep ocean currents. It was another milestone, showing that Hadal exploration is becoming more inclusive and diverse. The technology continues to improve. Triton Submarines is working on new designs, potentially allowing for deeper dives or longer endurance. Other companies and institutions are developing their own deep submergence vehicles, creating competition that drives innovation. The Hadal Zone is no longer unreachable. It's difficult, expensive, and dangerous, yes. But it's accessible in a way it never was before. And with that accessibility comes the potential for greater understanding, for systematic study of these extreme environments, and for discoveries that could reshape our knowledge of life, geology, and Earth's processes. Victor Vescovo's achievements demonstrated that determination, engineering excellence, and sufficient resources could overcome almost any obstacle. He turned the Challenger Deep from a legendary destination visited once in a generation into a place where multiple dives in a single year are possible. And on January 10, 2025, the U.S. Navy announced that the lead ship of the Explorer-class ocean surveillance ships would be named USNS Victor Vescovo, with his spouse serving as sponsor. It's a rare honor, recognition that his contributions to ocean exploration match those of the greatest explorers in history. The Challenger Deep has gone from mystery to frontier to destination. The journey from HMS Challenger's sounding in 1875 to Vescovo's 15 dives in the 21st century spans 150 years of technological progress, human ambition, and scientific curiosity. It's a story of pushing boundaries, of refusing to accept that some places are forever beyond reach. More than a century and a half have passed since HMS Challenger first measured unusual depths in the Western Pacific. In that time, humanity has gone from surface soundings with hemp rope to sophisticated submersibles that can visit the deepest point repeatedly. We've learned that the ocean floor isn't flat and featureless, but rather a landscape of dramatic trenches, towering seamounts, and volcanic ridges as complex as anything on land. We've discovered that life exists in places we thought uninhabitable. The Hadal Zone, named after the realm of the dead, is actually full of life. Strange, adapted, persistent. Amphipods as large as small lobsters. Snailfish with gelatinous bodies and TMAO-soaked tissues. Bacteria that recycle nutrients. Sea cucumbers crawling across sediment. An entire ecosystem functioning in darkness, cold, and pressure that would crush most surface organisms instantly. The Challenger Deep represents the absolute edge of what Earth can create. It's the product of plate tectonics operating over millions of years, the Pacific Plate diving beneath the Mariana Plate, dragging the seafloor down to depths that approach the limit of what subduction can achieve. If Earth were larger, with stronger gravity, trenches might be deeper. If it were smaller, they might not exist at all. The Challenger Deep is a consequence of our planet's size, composition, and thermal history. Only 27 people have visited the Challenger Deep as of 2024. Compare that to space. Over 600 people have been to space, orbiting Earth or traveling to the Moon. It's easier to leave the planet than to reach its deepest point. The pressure at the bottom of the Challenger Deep is more challenging than the vacuum of space. Building a spacecraft is simpler than building a submersible that can withstand 1,000 atmospheres of pressure. This reveals something interesting about exploration. We tend to look outward and upward, to the stars and planets, dreaming of distant worlds. But right here on Earth, vast frontiers remain unexplored. The Hadal Zone, comprising all the trenches deeper than 6,000 meters, covers an area roughly the size of Australia. Yet less than 1% of it has been mapped in detail. We know more about the surface of Mars than about the deepest parts of our own ocean. The reasons are practical. Deep ocean exploration is expensive, dangerous, and technologically challenging. Funding agencies and governments tend to prioritize space exploration because it captures public imagination and has geopolitical significance. Private individuals like Vescovo are exceptions, willing to invest their own resources in ocean science. But the deep ocean matters. It plays a critical role in Earth's climate system, storing heat and carbon, driving circulation patterns that distribute warmth and nutrients around the globe. The deep trenches are part of the subduction process that recycles Earth's crust, affecting volcanic activity and mountain building. Understanding the deep ocean helps us understand how our planet works. There are practical concerns as well. Deep-sea mining is becoming economically viable, and companies are eyeing the mineral-rich nodules that litter the abyssal plains and the metal sulfides around hydrothermal vents. Before we start extracting resources from the deep ocean, we need to understand what's there and what we might be destroying. The discovery of plastic at the bottom of the Challenger Deep should give us pause. For decades, we treated the ocean as an infinite dumping ground, assuming it was too vast to be affected by human activity. We were wrong. Our waste reaches everywhere, even to the most remote places. Microplastics have been found in the tissues of Hadal amphipods and snailfish, incorporated into the food web of the deepest ocean. Pollution isn't the only threat. Climate change is altering the ocean in ways we're only beginning to understand. Warming temperatures affect circulation patterns. Ocean acidification, caused by absorbed carbon dioxide, changes the chemistry of seawater. These changes will eventually reach even the Hadal Zone, affecting the organisms that live there. But there's hope in understanding. Every dive to the Challenger Deep, every sample collected, every organism studied adds to our knowledge. We're beginning to map the biodiversity of Hadal ecosystems, to understand the adaptations that make life possible there, to recognize the interconnections between the deep ocean and the surface. The Challenger Deep also serves as a natural laboratory for studying extremes. The biochemistry of Hadal organisms, their pressure-stable proteins and TMAO-soaked tissues, could have applications in biotechnology and medicine. Understanding how life adapts to extreme pressure might help us develop new materials, new drugs, or new industrial processes. And there's the question of life beyond Earth. If life can exist at the bottom of the Challenger Deep, under conditions that seem utterly hostile, Where else might it exist? Europa, a moon of Jupiter, has a subsurface ocean beneath an ice shell perhaps 20 kilometers thick. That ocean is under pressure, in darkness, cold. It might resemble the Hadal zone in some ways. If life exists there, it might face similar challenges and develop similar solutions. Enceladus, a moon of Saturn, also has a subsurface ocean, and geysers of water erupt through cracks in its icy crust, spewing material into space. Spacecraft have flown through these plumes and detected organic molecules, salts, and other compounds. Could there be life in Enceladus's ocean? The Hadal zone shows us it's possible. Studying extreme environments on Earth prepares us to recognize and understand life elsewhere. The adaptations of Hadal organisms expand our definition of what life can be, where it can exist, and what biosignatures we should look for when searching for life on other worlds. The technology developed for deep ocean exploration also has applications elsewhere. Pressure-resistant materials, advanced batteries, underwater communication systems, and autonomous vehicles all have uses beyond ocean science. Innovations driven by the challenge of reaching the Challenger Deep benefit other fields, from offshore industry to climate monitoring to space exploration. The story of the Challenger Deep is also a story of human ambition. From the Victorian explorers aboard HMS Challenger to Pickard and Walsh in the Trieste, from Cameron's solo dive to Vescovo's repeated expeditions, each generation has pushed a little further, achieved a little more. The deep ocean called to them, and they answered. There's something profound about reaching the extremes, about testing the limits of what's possible. It's not always practical or economically justified. But it expands the realm of human experience, proves that no frontier is permanently closed, and inspires others to attempt their own challenges. The future of Challenger Deep exploration looks promising. With DSV limiting factor, now renamed Bakunawa, continuing operations under Inkfish, more dives will happen. More scientists will visit the bottom, collecting data, observing life, mapping the seafloor in detail. Other submersibles are being developed by China, Japan, and private companies, creating a potential future where multiple vehicles can explore Hadal zones simultaneously. Autonomous vehicles, remotely operated vehicles, and robotic landers will supplement crewed dives, gathering data continuously and at lower cost. These machines can spend weeks or months in the deep ocean, far longer than any crewed submersible. They can collect samples, measure environmental parameters, and observe creatures in their natural habitat without disturbance. The Hadal zone will gradually give up its secrets. We'll catalog its species, understand its ecosystems, map its geology, and recognize its role in Earth systems. The Challenger Deep will become familiar, no longer a mythical place but a known location with documented characteristics. But even as it becomes familiar, it will retain its mystique. It's still the deepest point on Earth. It still requires extraordinary technology and courage to visit. It still represents an achievement to reach it, a frontier conquered. For most people, the Challenger Deep will remain distant, experienced only through footage, photographs, and descriptions. But knowing it's there, knowing it's been reached, knowing life persists in such an extreme place, changes how we think about our planet. Earth is more than continents and surface oceans. It's a world with depth, with hidden places, with mysteries that reward those patient enough to seek them out. And so we come to the end of tonight's journey. We've descended from the sunlit surface through layers of blue, past the twilight zone, into complete darkness. We've felt the pressure increase, atmosphere by atmosphere, until it became almost unimaginable. We've watched the temperature drop to just above freezing. We've touched the soft sediment at the bottom, 10,000, 900 meters below the surface. We've met the creatures that live there, amphipods with their transparent bodies, snailfish with their gelatinous tissue, sea cucumbers crawling across the ooze. We've learned how they survive, the biochemical tricks they use to stabilize proteins, balance osmotic pressure, and extract energy from scarce food. We've followed the history of exploration, from HMS Challenger's sailing expedition to Trieste's heroic dive, from Deep Sea Challenger's solo mission to DSV Limiting Factor's repeated visits. We've seen technology advance from hemp rope soundings to titanium pressure spheres, from gasoline floats to syntactic foam, from incandescent bulbs to LED arrays. We've understood the geology, the collision of tectonic plates that creates trenches, the subduction of ancient oceanic crust, the V-shaped depressions where the seafloor drops away to its absolute limit. We've grasped the timescales involved, millions of years of slow motion, centimeters per year adding up to thousands of kilometers of travel. The Challenger Deep is many things. It's a geographical location, a point on a map with precise coordinates. It's an ecosystem, home to creatures found nowhere else. It's a geological feature, the product of plate tectonics and deep time. It's a challenge, a destination that pushes human technology to its limits. And it's a reminder that Earth still holds mysteries, still offers frontiers, still rewards those who dare to explore. As you drift off to sleep, perhaps you can imagine yourself in a submersible, sinking slowly through the darkness, descending toward the deepest point. Feel the gentle motion as you fall through water. Notice the temperature dropping, the pressure building. Watch through a small viewport as the last traces of light fade away, replaced by absolute blackness. There's no need to be afraid. You're safe inside your pressure sphere, surrounded by thick walls of steel or titanium, protected by careful engineering. The descent is slow and peaceful. Time stretches out. There's nothing to do but sink, to wait, to experience the strange tranquility of falling through an ocean. And then, after hours of descent, a gentle bump. You've reached the bottom. Outside, illuminated by your lights, is a pale expanse of sediment, fine and undisturbed. You're at the deepest accessible point in the universe, as far down as you can go while remaining on this planet. It's quiet there, peaceful. The water barely moves. Nothing happens quickly. You could stay there for hours, observing, thinking, simply being present at the edge of the world. Eventually, you'll release your ballast and rise, returning to the surface, to sunlight and air and the familiar world above. But for this moment, you're at the bottom of the Challenger Deep, 10,900 meters beneath the waves, deeper than mountains are tall, in a place where humans have only recently learned to go. If you enjoyed this gentle exploration into the deep ocean, consider subscribing to the Slumber Science Society for more journeys through science and nature. Like this video if it helped you relax. Share your thoughts in the comments below. Your support helps others discover these peaceful explorations, one sleepy soul at a time. Until next time, rest well and dream of the depths.